Welcome to the new episode of the Recharge Zone podcast for season 5. We're welcoming back Marcus Gary. Glad to have you back on the podcast again this season. And just to recap, Marcus had joined us in season 3 for the ET, Not the Alien, where he discussed evapotranspiration, the eddy covariance tower at the EAA Field Research Park, and the research he was conducting. Welcome, Marcus.
Great to be here, Ann Margaret.
Today, he's going to share with us some recent projects that have been completed at the FRP, including a new monitoring well that was drilled and some of the network that includes other monitoring wells at the FRP.
That's right. This is kind of a companion podcast to our recent story in the news drop, which is titled A Quintet Network of Wells is Online at the EAA Field Research Park. So it's all about this new well that was drilled, and Marcus was directly involved, and so we want to get his take on that. So Marcus, you were involved in the drilling of the well and the coring project. Is that right?
That's right, Brett. It took quite a lot of time to get all that set up. There are a lot of logistics. It's a pretty unique project, so there aren't a lot of drillers who can collect those rock cores. And so there was really only one in the whole Central Texas area that was available. So we had to get on their waiting list. And that took some time. So the project was delayed a little bit, but once we got going, we got some really good results.
So it ended up, the project started in the middle of the summer, right?
It was brutal.
Brutally hot.
Oh, gosh.
We were out for 2 months coring and drilling and completing the well, and it was in mid-June through July, and it was over 105 most of those days.
Yeah, I was there for some of that, and it was extremely hot. Maybe you could share for our audience, what exactly is a rock core? What does that look like?
Sure. So there's a difference between just a well that's drilled and a core. So they're both holes in the rock or in the ground. Typically, they go down to the water table or below the water table. But when you drill a hole that's just for a well, you're crushing up all the rock into little bits, a lot of times into powder. It may come up with air or with some type of a fluid as the drill bit crushes up the rock into dust. So you don't have a real solid piece of rock. Whereas a core is actually a barrel. In this case, it was about a 3-inch diameter. That it's just like a hole saw, like if you're drilling into a piece of wood. Mm-hmm. And so it just cuts around the circumference of the hole as it goes down, and it pulls out what's in the middle of that core barrel up in different bits. So you can't just keep drilling continuously. You have a barrel. It's like a pipe that splits in half. And so as you drill down into the rock, the rock that's inside that core barrel will be in that pipe. And so you do it in sections, which depends on what's going on. Is the rock hard? Is it breaking apart? So they're typically about 10 feet long, but you don't always get 10 feet of a solid rock tube that comes out. So it's in pieces.
And can I ask you, what is the barrel made of? It can penetrate through all that rock?
Right. So the barrel is like a piece of pipe, and on the end of it, it's got a bit.
Okay.
And then on the bit, it's around the edge, it's typically got pieces of diamond.
Oh, okay.
Or tungsten. We had bits that had both materials, and we changed them out in different type of rock types. So the Edwards limestone was at the top of the core hole, so the top about 160 feet, where it was Edwards limestone, and below that is the Glen Rose. And so the Edwards limestone is much harder and is much more broken apart than the Glen Rose, so it's much more difficult to core. For instance, the rate that we were drilling down into the rock was probably about 5 times faster once we got into the Glen Rose than when we were coring into the Edwards.
Oh, that's interesting. Okay, one more question. So, the barrel, you said it's in 10-foot sections?
Correct.
So, is it like you drilled 10 feet into the Edwards and then 10? So, you would, and then y'all would go once that disappeared or once you got that out?
So, they would go and drill for some distance, so some number of feet. Sometimes it might have been just 1 or 2 feet, and they would stop because something changed.
Oh, okay.
And they would pull it up and verify that we were getting the rock still in the.
Oh, okay.
And so in the Edwards, because that rock was so much harder, we would typically just go a few feet and pull it up and check it at each time, because sometimes when the rock is hard and it breaks apart into pieces and this core barrel still spinning around, it'll still kind of break apart the rock.
Okay.
And so you're unable to pull it out.
Oh.
So that's called percent recovery. And so that how much recovery is a ratio of how many feet you go down in the hole, and then how many feet of actual rock sample you get. So if you go down 2 feet into the hole, and when you pull it out, if you only have 1 foot of rock sample, then you have 50% recovery.
Oh, okay. Interesting.
I think a lot of our users could probably visualize like an Arctic research station where they're pulling ice cores, and they pull these cylinders of ice.
Yeah.
It's kind of the same concept, but much longer period of time. And so you're looking at these rocks, and you can see things like the vugs in them. You can see cracks and
Fossils?
fractures, maybe
That's
fossils.
sure.
You can see, how hard the rock is. So it was really neat to see that change between the Edwards and the Glenrose, like Marcus mentioned. Of course, it went a lot faster, but that's because the Glenrose had fewer fractures and it was softer rock.
Right, the Glenrose has a lot of clay in it, so it was
Interesting.
it's much softer than the Edwards, and because of that, we would have a higher percentage of recovery of the rock in the Glenrose. And so sometimes once we got down into the softer rocks of the Glenrose, they could actually go down the full 10 feet of that section of pipe and pull it out. And so we did have almost 100% recovery of a big 10-foot section.
Oh, interesting. And is this an Edwards well or a Trinity well?
So it is a well that is drilled through the Edwards. It's what we call a drill-through well. The water table at this particular location is almost right at the contact between the Edwards and the Trinity.
Whoa.
So the water is all in the Trinity Aquifer, but you have to drill through the Edwards to get to it.
Okay.
So we had to get a permit, not even though we're the regulatory entity for the Edwards.
Yeah.
We also had to get a permit from the Trinity Glenrose Groundwater Conservation District, because the well was in their jurisdiction.
Wow. Okay.
So even though the FRP is on the Edwards Aquifer Recharge Zone and you have Edwards limestone at the surface, the groundwater, because it's far enough north, is actually Trinity groundwater. So you go a few miles south, and then it transitions to Edwards groundwater.
Yeah, you're even a little east as well. So just because of the direction of the faults and how the fault in that area offsets the Edwards and the Trinity.
So even though it's situated on the recharge zone, most likely wells drilled in that area are not Edwards wells.
That's correct.
Oh, wow.
Just because the water table's below the base of the Edwards limestone.
Okay.
So
Okay,
it's
that
just
makes
below
sense.
that elevation.
One of the reasons for drilling it is because, all the wells out there are Trinity, but even in those wells, there are differences.
Oh.
So the geochemistry is a little different. The water levels react differently. So that's part of the impetus for drilling this new well was we wanted a well where we had kind of a data gap to realize or visualize some of these differences just in the Trinity Aquifer itself.
And nice that you mentioned the other wells at the FRP that we monitor. So we've got 3 or 4 other wells. I say or 4 because one of the wells we didn't drill. It's a very deep well. It's called the Lumberman's Well. And it's over 1,300 feet deep.
Oh, wow.
So it's 1,000 feet deeper than this well that we just drilled.
Really?
With the core. It's only a few hundred yards away. However, it's not sealed or cased between units. So it goes all the way to the lower Trinity Aquifer, so the very bottom of the Trinity through 1,000 feet of Trinity rock. And it's in the Trinity Aquifer is really 3 aquifers. So there's an upper, middle, and lower Trinity.
Okay.
And they all have very different characteristics. Since this hole is open, meaning it's not cased or sealed, it's all mixed together. So so we're collecting water level data there. We can collect water samples and measure the geochemistry there, but we don't know where that water's coming from, right? 'Cause it's all getting mixed together. So one of the things and the unique benefits to drilling this new well with the that we cored, and then we completed the well, is we had control of how that well was completed. So we knew how it was sealed. And so one objective that we had is we wanted to make sure that this well was completed to the same standards that any other permitted drill-through well would have.
Oh.
So, meaning it's sealed off from the Edwards, from the Trinity, using the same standards and the same criteria to determine how that well is completed. So we know that when we collect a water sample or we get a water level, we're getting water characteristics that are representative of that top layer of the Trinity Aquifer.
Okay, the upper.
The upper
okay.
Trinity, right. So in the future, we can see if we drilled wells nearby that were just in the Edwards, we might be able to see if there's a connection to it. That so for instance, in the northern segment, or the Barton Springs segment of the Edwards Aquifer, they drill these wells that are called West Bay wells, or a multi-port well, where they can complete the wells to measure specific characteristics of all these fine layers.
Wow.
Even though it's just one well, they can see what's going on at like 15 different intervals.
Wow.
And so they use that information to, and they observe that the very top of the Glen Rose operates very similar to the Edwards, and so they've adapted their rules based on those observations.
Really?
They have.
So this data. So when you're looking at these five, it's five, right, at the FRP, these 5 wells, you're looking at water level data, right?
That's one of the characteristics.
And like what are the other characteristics that y'all look at?
We look at the water chemistry. So we sampled all the wells, I think monthly, Brent. So very high frequency of sampling for major ions that are in the water. So how much calcium or sodium or any of those major elements that are naturally in the water. Also bacteria, different emerging contaminants like pharmaceuticals and PFAS and things like that.
Okay.
So all those types of things are sampled for regularly. We also have a continuous specific conductivity in some of the wells. And so that tells us how fresh the water is. So whenever we get a big recharge event, of course, rainwater is very fresh. It has very few minerals, if any, that are dissolved in it. So when that water recharges into the aquifer, it makes the water that we're observing in the wells become fresher or change that specific conductance. So we can see how the aquifer is responding to those types of recharge events.
Wow.
In real time. So
Yeah.
these are all connected to our real-time telemetry network.
Oh, they are? Oh, cool. So like, and then other groundwater districts might potentially use this information too for other things?
Sure, we're not the only ones that monitor these types of wells. So, this is really the primary tool that we have to both understand how the aquifers respond to recharge, how they respond to pumping, and how those trends are propagated through the aquifer over long time periods.
Yeah, I mean, for instance, the Trinity Glen Rose Groundwater Conservation District in Bear County monitors the Trinity Aquifer, so they're definitely interested in our data.
Okay.
And we collaborate very closely with all the groundwater districts. In this particular area, we are in the jurisdiction of the Trinity Glen Rose in Bear County, but you go just across Cibolo Creek and you're in the Comal Trinity Groundwater Conservation District. And so we work closely with them as well.
Nice. Kind of shameless plug for our website. In the maps section, we have like all of the groundwater conservation districts mapped around us. And you can just see how many there are.
There are a lot. There's probably 7 or 8 that directly touch us, jurisdictionally, and a couple more that are included in the contributing zone. And so most of the groundwater conservation districts that are in the contributing zone, which would be in the Trinity Aquifer, are in the groundwater management area 9. So it's a group that works with the Water Development Board. Brent, you can speak to a lot about that. You coordinate.
We should have a whole podcast just on this part.
That's right. But anyway, I was just at one of their workshops a few weeks ago, and one of the main discussion points was coordinating data from monitoring wells and figuring out the best way to interpret those data, so they can use that for defining what they call desired future conditions, or what they want the aquifers to look like
interesting.
in the future, in the next 50 years. And so this is a process that's directed by the Texas Water Development Board. But these water levels in wells are really the primary indicator of how they, plan for what the aquifer is going to look like in the future.
Interesting.
It's really amazing, where we've come from and aquifer science and aquifer research. I mean, just in the 1970s, the courts decided that, groundwater was too mysterious to really regulate. So we've gone from that just in the 70s to now understanding the different units and the different various aquifers, and now we're learning about how they flow and how they recharge and things like that. So yes, we're still learning, but looking back from where we've come from, we've come a long way, and we hope to go that much further in the future.
Yeah,
absolutely.
And okay, so I have a question. So the research that's happening at the FRP, like I know some of the things that we've talked about on the podcast, like the evapotranspiration stuff, and then the Saturo, if I'm saying that correctly, and then the berm and swales, like the land management practices, and then now the research that with these monitoring wells, do those all fit together in some kind of way, or are they like separately done?
That's a great question, right? And so that's one of the most difficult questions that we cope with as scientists. How do we fit all these different data sets together? Because fundamentally they are all part of the water budget. So it's just like your checking account or your savings account. How does your checking account relate to your savings account?
True.
So those same kinds of questions. And these are just different aspects of the water budget. And so we have to understand how to conceptualize the system, and how does evapotranspiration relate to recharge? And how does recharge relate to change in water levels in a well, or the stream flow in Cibolo Creek? How do all these different factors fit into it? And so the first thing that you do is you have to develop an accurate conceptual model to to know how the system works, and then you have to figure out where you need to collect those data to complete that water budget.
So it's the water budget. Okay.
Right, and there are lots of parts of the water budget that we don't really have a good idea. So how water percolates down through the soils and in the upper part of the rock, which we call the vadose zone, and then down to the aquifer, that's a really hard location to monitor.
Interesting.
And so we're trying to develop novel ways to quantify that. So we have these different boreholes that are only about 30 feet deep that are around the berms and swells. And we have a tool that's called NMR, a magnetic resonance. Yeah. And you can drop it down and measure the water, the volumetric water content. And so you can see when the soil is really dry or when it's wet. And so for the last year, it's been really dry. And then it rained 5 or 6 inches, and then we started to see water moving down through the soils. And we can kind of compare how those characteristics are different within the berms or above the berm or below it.
Okay.
And see what those effects are. But all of that is tracking that water as it moves downward through the upper subsurface.
So we're trying to calculate every variable of the water budget out there. So evapotranspiration, runoff, infiltration, recharge, rain, weather data. So it all does work together in one complicated puzzle.
Right. It's kind of like having, Disney Plus and Amazon Prime have automatic debits in your account, and you forget about them.
Yes.
So we got to, kind of figure out where all those are, and then figure out how much those debits are.
That is so interesting. And is that where the modeling comes into play?
Right. That's how you fit it all together.
Okay.
Eventually, you conceptualize the system, and once you're comfortable with that, you're capturing all the aspects of the water cycle, then we characterize it with the data that we're collecting, the numbers, and then those can get put into a model that fits them all together.
Oh, interesting.
And you could scale it up. So this is what happens at our site, but what if we had 1,000 sites like our site? What effect would it have on the aquifer?
Or we can extrapolate from detailed studies at our site
Uh-huh.
and make assumptions that it's, these are other areas that are similar. So the same model that works at our site would work at other locations.
Nice.
So then we can scale it up to larger, regional scales.
And then these models that you all have to they make projections for the future too, then I would assume, right? Or they could.
So yes, there are models, groundwater models, like our ModFlow model, which is used for the HCP, has models that feed into that related to recharge. And that's one of the things that our modeling team is working on right now, is how to develop new recharge models that can incorporate a lot of this new research that's going on. Because in the past, we just didn't know so many things, so the models used a lot of assumptions or overgeneralizations of some of the different hydrologic processes that are involved in the water budget, and so they weren't as accurate. And so we're trying to figure out how to conduct these studies to help us understand the processes in more detail, so we can implement those into the models.
So it's like it's the real world applicability of the research that you're doing for the HCP stuff, like what you're
eventually
researching.
it could translate to those types of decision making tools for sure.
I mean, these models are only as good as the data that you put into them.
Okay.
So
Right.
our job is to make that data as accurate as possible.
Right. Yeah, if you're using models with poor data, I mean, the models just, in the best case have, uncertainty values that may be, 10% or 15%. But if you're inputting data that are only 15 or 20% accurate,
I see.
then your models may be only 40% accurate. And then what does it tell you?
Yes,
It's
true.
It could give maybe false confidence in what you would expect conditions to be in the future.
That makes sense. And so I just had this question, but so what we're doing at the FRP, is it unlike, would you say, some other things that have been done? Like, is it kind of maybe the first of its kind, like the robust nature of all the research that y'all are collecting?
It fits into a pool of projects called Managed Aquifer Recharge, or MAR projects. So there are other projects around the nation that aim to do similar things, but it's one of the first of its kind to try to quantify the value of these natural infrastructure earthworks type projects. So there's a lot of qualitative data out there, but there isn't a lot of quantitative data that put numbers behind the possible benefit of these features.
But it is an emerging kind of realm in hydrologic research, and to see what the effects of these MARs are, these different tools to help manage aquifer recharge.
Yeah.
Yeah.
It seems like a dream. If I was a researcher, I'm like, because it's like the best of everything,
So,
right?
one of the unique things about the FRP is, since the EAA is the steward and the owner of the property, that we have more direct control of what happens there. So it really speeds things up. A lot of times these types of projects, where there's more complexities of people involved, take a really long time to get going. I mean, we've only been going at the FRP really for about 4 years. And it's one of the most heavily instrumented areas that I know of.
Wow.
So,
That's amazing.
And the pace is picking up too.
Yes.
So but like you said earlier, we got to figure out how all these different bits of data that we collect fit together to answer those questions on the water budget.
Marcus, we've truly enjoyed you being here today, and of course talking about all the research that's going on. It's pretty exciting, and I'm glad I've been part of it too, and glad we can cover it for our general audience and our listeners to hear more about it. So I really appreciate you being here.
Absolutely. Anytime. Look forward to the next time and chat about the next big project we have going out there.
You bet. Until next time, y'all.
Thanks for tuning in to this episode of the Recharge Zone podcast. Have questions, ideas for topics, or things you would like to share with us? Well, reach out to us at rechargezone@edwardsaquifer.org.